Okay, so your graded exams are here. If you are in the class and you haven't picked them up, you can, of course, come and pick them up. The first thing you want to do today is to decide what you want to do with the exam 1 grades, right? Do you want to have like 20 bonus points, take these exams home and solve them, bring them back to get the maximum of 20 bonus points? Or do you want to essentially use the part of final exam grade as the exam 1 grade? Okay, are we clear on what the 2 options are? Okay, so we have 2 students online. I guess we can wait, like give it another like 2 or 3 minutes, 5 minutes, and then decide about it. If you have any specific questions about your exam, this is the time to ask. I haven't uploaded the grades yet. I know I told you I'm going to upload it yesterday or Tuesday, but it completely escaped my mind. So those of you who are online, I guess you have to vote with not knowing your exam grade, or if you have a friend in class, you can tell them to look up your grade and tell you, so you can make an informed decision. You can like have an informed one. Is there any questions? Do we have anyone who has an issue with their exam? You don't have to say your issue publicly, of course. You come here, we talk about it. But let's actually begin the lecture, at least an introduction to the lecture, and then we'll come back to it. Let's like do 5-10 minutes of lecture, and we'll come back to it. So we are going to start chapter 5 today. Chapter 5 is essentially the integral analysis of the flow. I think that's not the title that your book uses, but that's effectively what we are going to do. So we are going to use the Reynolds transfer theorem that we saw the other day, we learned about the other day, and find the governing equations of the fluid flow. This will be the most general types of equations you are going to see, and they will apply to any type of flow. Of course, for our specific use, we are going to simplify them to make the situations you want to apply them to a little simpler. So at the end of this chapter, I expect you to understand the governing equations of the fluid flow, which are 3. There are 3 main governing equations, or 3 types of governing equation. Conservation of mass, and at least 2 of these equations we have seen before, but they're just a simpler type of it. Conservation of mass, a momentum equation, and the energy equation. Momentum, the general form of momentum equation by itself is 3 different equations, 3 sets of equations, mainly because forces and momentum are directional. Like momentum itself is a vector, right? So we effectively have, if you are dealing with Cartesian coordinate system, we effectively have 3 different equations. Okay. But in general, what you're going to get from these equations, the most general forms of them, of course, is the 5 equations. But in fluid flow, we have 6 unknowns. The most general type of the fluid flow. The velocities, pressures, and all of the other different unknowns that are out there are 6. So we need 1 more equation for the most general type of fluid flow to be able to solve, to be able to have an understanding of what's going to happen, to find the velocity distribution and all of those things. So we always are going to need an extra equation. That equation in gases is usually the ideal gas law that you have used before. And in liquids can be the state equation for the liquids, different types of equations that you can add to the governing equations of fluid flow. But the 6th equation is not the focus of this chapter. We are mostly going to focus on the conservation of mass, momentum, and energy equation. Today, we only are going to focus on the conservation of mass part of the equation. And then the next lecture, we are going to do the momentum and the energy equation. But you have seen a simple, as I said, you have seen a simpler form of at least these 2 equations, the conservation of mass and momentum equation. For conservation of mass, the simplest form was between 2, and let's say we are in a duct, point A, point 2. We can say A1, B1, if the density is constant, is equals to A2, B2. So the cross-sectional area of the point 1 of the surface 1 multiplied by the velocity at the surface 1, if the velocity distribution is uniform, which means that the velocity is the same throughout the surface. That multiplied by area is going to be velocity, uniform velocity at the surface 2 multiplied by the cross-sectional area at the surface of the surface 2. Okay? And the momentum equation example that we have seen is the Bernoulli's equation. We made 4 main assumptions. That was part of your exam as well. What are those assumptions? You needed to answer that part. And if you make that 4 assumptions, your momentum equation reduces to the Bernoulli's equation. Okay. What are those 4 assumptions? Does anyone remember? No one? Incompressible, along a streamline, inviscid, and a steady state, right? These were the 4 assumptions that we needed to make to come up with the Bernoulli's equation. Okay, so since we already have the intro, and what time is it? It is already 2:57. So we have given enough time to people to show up to class. Let's talk about the exam. Let's actually vote on this. We have 2 options. Get 20 bonus points if you bring back the correct solutions to exam 1, like submit correct solutions by Tuesday. That's Tuesday, 23rd. Okay. Or option 2 is that I can use your answers to questions from chapter 1, 2, 3 on final as like your graded answer, your grade, whatever, as your exam 1 grade. 2 options. So those of you who are in class, you have seen your grade by now. Those of you who are online, you can send send a text or whatever to your friends in class and get an idea about your grade if you already don't know it. So, do we have any comment, any questions before taking a vote? Any inputs? Is there anyone who wants to add an option to the table? No? Okay, let's take a vote. Who wants to go with option 1? Okay, so I guess a lot of people in class. We have enough votes to cover for even the online people in class. Everyone in class except for a couple of people, 1 or 2 people went for option 1. So this is what we're going to do. Take the exam 1 home and bring back, submit your answers to all of the exam 1, not just the parts you got right. I mean, of course, you can just copy the parts you have gotten right in your submission. But I want to see a submission that has the answers to problem 1 through 11, all of it. The correct answers, of course. And if you have the correct answer for everything there, you will get up to 20 bonus points. Okay? Is this clear? Yes.
Are we turning it into you in person?
Yeah, you could. What do you mean by that? I mean, like.
Well, like, for the homework, how we turned it into you, and then now it's.
That's something I can do as well. Yeah, I can open a portal, like create a portal on Blackboard. That's another option. It doesn't really matter to me, whatever you prefer, but I want everyone to follow the same thing. So if all of you want to submit online, I can create a portal. If not, you can submit it. Who wants to submit online? Who prefers to? Okay, so we're going to create a portal on Blackboard. Guess we are going to save paper, which is always a good thing. Okay. Let's see actually if there's anything I want to talk about on your exam. Do we have any specific questions about the exam? Is there any problem on before moving on, is there any problem on the exam that you have no idea about and you want me to go over? So essentially, the idea here is not another exam. It's just to help you with your grade. So I'm not going to check. I mean, you can work together. You can solve the problems together. But I want you to understand the solution. You can, of course, come to my office and we can solve the problems together in my office, right? But don't go online and copy the solutions, right? If you do so, I'm not gonna deduct any points because most probably I won't figure it out, or my grade I won't figure it out if you have done so or not. But again, the goal here is for you to learn, right? So if you want to solve it together, you're welcome to do so. If you want to come to my office and ask me questions, you're always welcome to do so. If you want to talk to your seniors and ask them to help you with the solutions, you're of course welcome to do so as well, but don't copy the solution from somewhere or from your friends, right? So in that spirit, is there any questions on this exam that you have no idea about or you don't know why? Yes. Number two. Okay. Yeah, let's go over. Let's actually do this. I think it's a good idea to do this. So number two. Number two, you all have access to the exam, but I'm going to read through the text of the problem anyways. You were asked to determine the pressure increase expressed in pascals required to reduce the volume of seawater by 1%. So pressure increase required to change the volume. Whenever you see pressure increase and a volume change together, or density change for that matter, it's essentially whenever you have volume change, you are going to have density change, right? That's the idea. Density is equals to mass divided by volume. Your volume is changing, density is changing. Whenever you see this type of thing, the first conclusion you have to make is that your flow is not incompressible. Because by applying pressure, you are changing the volume. By changes in pressure, your volume is changing. Which is the assumption, the incompressible assumption, is the assumption we make for most part of the course. Unless we are deriving this general, we're finding these very general equations, which we don't really use them, right? In their general format, we usually simplify them. Okay, so, and the only tool we have to deal with a compressible flow is the bulk modulus. This is the only tool we have ever learned about, right? Bulk modulus. What was the formula for bulk modulus? E of V is equals to negative changes in pressure, dP, divided by changes in volume, multiplied by your volume. It can be initial or final volume. That doesn't really matter. Or we can actually have the same equation in terms of density. So dP divided by d rho divided by rho. Okay? The difference is just a negative sign. This is something you had on homework. There was a problem on homework 1 that dealt with this type of analysis, the bulk modulus. Okay, bulk modulus tells you how compressible your fluid is. Since gases are usually more compressible, it is easier to compress gases. Bulk modulus is going to be smaller. So the amount of pressure you need to change the volume is lower, right? For seawater, bulk modulus is very high. We actually have the value of the seawater bulk modulus in the book, but you didn't need to have the value, and the value wasn't given to you. You could just assume that this is constant, okay? Just a constant value, just a number, whatever, 1 million, whatever. So we want to find the changes in pressure. So let's rearrange this equation for pressure. dP is going to be equal to negative EV dV divided by V, right? So that's the equation we want to use in this problem. But we are told that the volume is going to be reduced 1%. So changes in volume is 1% or 0.001 of your initial volume, right? That's an information that is given to us. And the volume is going to reduce, so negative 0.001 or whatever, right? So negative dP equals to negative AP1. We're going to substitute this for dV multiplied by divided by V. These cancel out, so you don't need to know the volume. The only parameter you need to know is E of V, or the bulk modulus, which you could have assumed just a constant number for it. It's just so, and this is a negative sign actually. So the amount of pressure increase has to be 1% of your bulk modulus. And that is the bulk modulus of seawater. And this is an equation this is a problem most of you got wrong. This is not a very hard problem. You have the equation. As long as you understand this part, you can easily find the answer to it. Right? Just essentially 3 lines. Right? And if you have any idea on why most of you got this wrong, please share with me. If not, we can move on to another question if you have any. Do you have any idea on why most of you got it wrong?
I didn't go over a problem like this for studying.
Okay.
That's why I got it wrong.
Okay, I see. But we had something a little more complicated than this, but use the same equation in the homework, right? Okay. So this tells you for the exam 2 and final exam is that this tells you that you have to make sure you understand the homeworks by heart, right? You understand everything about them, right? Not just how to solve that specific problem, but you understand the concepts behind that equation, behind that whatever, behind that idea, the whole thing, right? Okay, so let's move on. Do we have any other questions that you have no idea how to approach, and you think it is not bad? It is not a bad idea for us to go over. When you don't ask any questions, it's telling that you knew all of the answers, but you got it wrong for another reason. So you are always welcome to yes.
Number 1.
Number 1, okay. Okay, let's do number 1. Let's actually do this. Let's solve all of them, huh? What do you think about that? Then you have the solution. Hopefully you understand when I solve them for you. If you didn't understand them, you can always come back to my office later. And then just submit the solutions, get 20 bonus points, huh? Let's do all of them. So number 1 is telling us the following equation is an expression of Newton's second law in which the force due to a pressure gradient is required to be equal to and in the opposite direction to the viscous forces on an infinitesimal particle of a fluid, resulting in the particle moving at a constant velocity. The first part of the question was just extra information. We don't really need that. Show that the equation is dimensionally homogeneous. Dimensionally homogeneous. Okay, and this is the equation. 0 is equals to negative partial p partial x plus mu partial squared u partial x squared. What does this mean? To check whether an equation is dimensionally homogeneous, we essentially have to check whether all of the terms there have the same dimension. This 0 here is a dimension scalar, right? Because the other part has dimension. So we can assign any dimension to that number, right? But that doesn't help us with the solution. So we're going to move this term over the other term to the other side. to the left-hand side. Partial P partial X is going to be equal to mu partial squared U partial X squared. So let's see what is the dimensions of the left-hand side, and then what is the dimension of the right-hand side. This partial operator itself doesn't have any dimensions, right? This is something hopefully we knew from physics or basic physics or mathematics, right? So partial operator itself doesn't have any dimensions. Then we have pressure. What is the dimension of pressure? Pressure is force per unit area. So newtons per meters squared divided by length x meters in SI. You could have done the imperial units as well. Okay. So left-hand side, the dimensions are going to be newtons per cubic meters. Okay. And this other, we have on the right-hand side, RHS, we have viscosity with the dimensions of newtons second per meters squared. The dimension I gave you in class, right? And then we have the second derivative of velocity with respect to x squared. Partial operator, dimensionless, so it doesn't really matter that it says partial squared, right? Second derivative. What is the dimension of velocity? It is meters per second, right? And then what is the dimensions of x squared? It is meters squared. Second will cancel out. This power here will cancel out with the meters in the numerator. So you'll end up with newtons per cubic meters. Right-hand side, the dimensions on the right-hand side is equal to the dimensions on the left-hand side. So dimensionally homogeneous. Okay. So as we are solving this, if you know or if you have any idea why you may have gotten this problem wrong, please go ahead and share, okay? Like I heard one person told me that they didn't know what dimensionally homogeneous means, okay? Which is an understandable thing not to know, right? I can definitely understand that. If that is the problem, you definitely have to ask this from mid-due in the exam, right? There's no problem with not knowing this. Whenever I ask you to check whether something is dimensionally homogeneous, I'm essentially asking you to check whether it has the same dimensions. All of the terms have the same dimensions. Okay? So, and we have already dealt with problem 2. Let's do the problem 3. Okay. So problem 3. How do you calculate the height of fluid in a capillary tube? This is from chapter 1 of the book. Actually, I usually forget the correct form of equation myself. Okay. So this is from the chapter 1 of the book. When we talked about surface tension, right? When we are talking about this, right? A capillary tube, how do you determine this height? We actually had a whole analysis on this force balance analysis, and eventually came up to this equation for it. 2 multiplied by the surface tension coefficient multiplied by the cosine of the contact angle divided by, keep forgetting this, gamma r. Okay, or rho gr. That's the only answer you should have given to get the full credit. The other question, so next one, question 4, is asking us what is Pascal's law. This is from the beginning of chapter 2. If you have the book in front of you, you can check. That's page 40, 2.1, pressure at a point. The idea of the Pascal's law was that pressure on a point is equal in the same direction, in all directions. Pressure on a point is the same in all directions. In a point of fluid. So essentially, pressure on a fluid particle depends on its depth and where the particle is located compared to the free surface. But it doesn't really matter on which direction you are looking at that particle. The pressure has to be the same all around that particle, right? That was the Pascal's law that we talked about at the beginning of chapter 2. And for part problem 5, that is part of the, I don't remember the exact location, but that is part of the chapter 3. Okay. The dynamic, define the dynamic, a static, and a stagnation pressure. The dynamic pressure, let's start with the static pressure. A static pressure was the pressure you felt when you were moving, when you were sitting on a particle in the fluid, right? That's 1 atmosphere or whatever. Right? The stagnation pressure was the pressure where you felt if you brought down the fluid velocity to 0 isentropically. And the dynamic pressure is essentially the difference between the two. We use Q infinity or Q for this. P is stagnation minus a static pressure. Okay, which can be calculated using 1/2 rho v squared. Dynamic pressure is not a real pressure, it's just a definition. It's just a name we have given to this value, 1/2 rho v squared. We call it dynamic pressure because it's a direct function of velocity. Okay, so that's problem 5. Problem 6, what is the center of pressure? Center of pressure, that is the pressure, is the point, center of pressure is the point at which the forces pass from it. Forces pass through this point. So force, hydrostatic force, passes through center of pressure, this point. Or we can say the total moment around the center of pressure is 0. So sigma m around Cp is 0. So to understand this better, let's say we have a free surface. And this is your pressure distribution. The idea was we can replace all of this pressure distribution with a force, right? How did we calculate that force? We calculated rho g of the centroid, so gamma of c, right? And we calculated rho g multiplied by the height of the centroid, or depth of the centroid, right? But we said this force does not pass through the centroid. It does pass through the center of pressure, right? And the depth of that center of pressure was y of r, which was a function of y of c and the moment of inertia divided by y of c multiplied by the area, the cross-sectional area. This was the equation we had for it. But then you don't need to mention the equation as long as you mention these 4 words. You would have gotten the correct. You would have gotten all of the grain. Problem 7, what are the 4 assumptions necessary for the Bernoulli's equation? The flow has to be incompressible, has to be steady, has to be along our analysis has to be along the streamline, and the flow has to be inviscid. I saw one person, or a couple of people actually, that's problem 7, right? Wanted to say Immersed, but didn't know the word. We had different variations of this word. So this is the word Immersed, which essentially means that we are neglecting the effects of viscosity. A lot of people, instead of saying Immersed, they actually mention this one, that they have to neglect viscosity. Okay, so that's one condition. Then it has to be incompressible, a steady state, along a streamline. Problem 8, comment on the stability of an immersed body. What are the different types of stability? If you recall, that's actually from chapter 2, I guess. We talked about an immersed body. We talked about the buoyancy force, right? Where the center of gravity is located. Let me actually find this. I think it was part of chapter 2. Or was it chapter 3? I don't remember. We had these pictures of an immersed body. Here, yeah. Chapter 2. Let me use let me actually show it to you here. Page 74. Give me 1 second to find this page. Okay. Oh, you don't see anything? It was working before we came to class. Just forget about it. It is page 74 of the book, where we had the center of gravity and the center of pressure, right? We had the relation between the two. And if we said that if their location changes, then your type of stability changes. We have 3 different types of stability: neutral, stability, stable, and unstable, essentially. Neutral was that if you put some force on the immersed body, then it would stay at the location, at the changed location. If it was stable, if you change its location, it would have come back to its original place, right? Do we remember this? Okay. So yeah, that's question 8. That was the only one of the descriptive one that you had to explain. And question 9. We are told that a layer of water flows down an inclined fixed surface with the velocity profile shown in the figure below. Determine the magnitude and direction of the shearing stress that the water exerts on the fixed surface. So we have this fixed surface. right? And we have a velocity. This is not a free surface. We have the velocity distribution like this. Velocity is given to us. U divided by U is 2y divided by h minus y squared divided by h squared. H and capital U you're supposed to assume that these are constant numbers, right? You're actually given those numbers. U is 0.2 meters per second and h is 0.1 meters. We are told to find the value, magnitude of the shear and the direction, the shear stress and its direction. We have this equation for shear stress. Tau is equals to mu du dy. And we are looking at the shear stress at the wall. So where y, this is the y direction, is equal to 0. Some people are really confused with the inclined surface. Just have to keep in mind the choice of coordinate system. If you are not already told what is the coordinate system, the choice of coordinate system is actually your choice. So you can have a coordinate system in this direction, y, x, right? So there were a couple of people who actually treated this as a linear velocity change from 0 to h, right? And then said tau is equal to delta u, which is capital U minus 0, divided by delta y, which is h, right? The reason we can't do this here is because the velocity distribution is nonlinear, right? So the derivative is not equals to delta u delta y, right? But we are given the velocity distribution, so we can take the derivative very simply, right? So we have to take the, let's actually simplify this u. Let's make this u. Take the capital U to the other side. We're going to get 2u y divided by h minus u. This is capital U y squared divided by h squared. Okay? So we want to take the derivative of this equation with respect to y. We have to take the derivative of first one first, the first term first. Derivative of 2uy divided by h is going to be 2u divided by h, right? That's the simple derivative of dy dy, right? Which is 1. So let me actually write it up here. 2u divided by h minus, and the second one, this part is going to be just a constant value. Derivative of y squared with respect to y is going to be 2y. So 2y divided by h squared y. And this changes from 0 to h. Okay. So if you plug the values in, you're going to get 2u minus 2u divided by h, 2u multiplied by h divided by h naught. That's for part h. And if you plug in 0, so you plug in 0, this is for the h part. And then you plug in 0 for y. You're going to get 2u divided by h negative minus 2u multiplied by 0 divided by h squared, right? This part, they cancel each other out. This part is 0. For your shear stress, you are going to end up with tau is equals to negative 2u divided by h. That's it. That's multiplied by mu. Sorry, forgot the mu. Multiplied by mu. So plug the values in. You were given the mu, you were given the u and h. You plug the values in, you calculate the shear stress. But how can we determine the direction? It has a negative sign, which is telling you that the direction of the shear stress is in the opposite direction of the capital U. So direction of the shear stress is going to be in this direction. Okay? And question number 10. We are given an airfoil, which is a 2D cross-section of a wing. And air flows over the airfoil shown in the figure below. Sensors give the pressure shown at points A, B, C, and D. So we have the pressures at these points, A, B, C, D, wherever they are. And the air density is 0.002 slugs per cubic feet. So rho of air, 0.002 slugs per cubic feet. Okay? And we want to find the air velocities just above those points, which essentially means that we want to find the velocities at these points, right? VA, VB, VC, VD. We are also given the V naught, which is the velocity of the free air stream. This is 100 miles per hour. We are given the P naught. The pressure here, any point here, is 13.2 psi A. So how can we solve this problem? We have the pressure at this point, pressure and velocity at this point. We also have the pressure at these points. We want to find the velocity at these points. The first thing you need to do to make sure that your problem is dimensionally homogeneous, you have to convert this to inches per second, right? Because the pressure is psi, right? So you have to make sure you know how to make that conversion. I don't have the numbers here with me, but just have to make sure you make that conversion, right? Convert to inches per second. That's the first thing you need to do to make sure you are dimensionally homogeneous. Okay, and for the next part, let's call this point A, or point not. We actually have it. The only thing we have to do for this problem, to solve this problem, is to write the Bernoulli's equation for point 0 and A, then point 0 and B, point 0 and C, point 0 and D. Or we can write it between point 0 and A, then point A and B, point B and C, and point C and D. Any points would work fine, should work fine, should give you the same result. Right? So what is the general form of Bernoulli's equation? P naught plus 1/2 rho V naught squared plus gamma Z naught, right? Is equals to P1, PA, let's do point A first, 1/2 rho VA squared plus gamma ZA. We can safely assume that the elevation doesn't change. And you also haven't given any information, you weren't given any information about the elevation, so that is what you need to do to solve the problem. So 1/2 rho V naught squared is equals to PA plus 1/2 rho VA squared. You can write this equation for the other 3 points. We have P naught, we have V naught, we have the pressure at each point. Right? We're given the pressure at each point. Plug that in, you find the velocity in inches per second, right? But yeah, and that will be it. If you want, you can convert it back to miles per hour, but you don't need to. Is there any questions? Okay, problem 11. We have two pipes that are connected to each other by a manometer, as shown in the figure below. Determine the pressure difference between A and B. So we have A, and there is this pipe. A, B. Okay. We want to find, we are given these. Inside the manometer, we have a different fluid. This is 0.6 meters. This is 0.5 meters. And this is 1.3 meters. Okay, we want to find PA minus PB. Let's start from PA and go down, right? Let's actually start from PA and come to this location. The idea was, if the same fluid has the same height, then the pressure is going to be the same, right? So the pressure at this point 1 and point 2 are the same. What is the pressure at this point 1? Since we are moving down from PA, pressure at point 1 is going to be higher than the PA. So we're going to get PA plus gamma H, right? That's gamma. What do we have there? Water. Gamma of water multiplied by H. This H here is 1.1 meters. Okay. And that is equals to P1, which has to be equals to P2. Okay. Let's look at the other side. Here we have this location, right? Let's call it 0.3. And then on the other tube, we have this 0.4, right? The pressure of 0.4 is equals to the pressure of 0.3. And here we are moving up. So pressure is decreasing. So pressure at 0.4 is going to be equal to PB minus gamma of water multiplied by whatever this height is. That's 1.3 minus 0.5. Okay, so 0.8 meters. We have the pressure at 0.4. We have the pressure at 0.3. And what is the relation between pressure at 0.3 and 0.2? It's just moving inside the same column. Pressure at 0.2 is going to be higher than the pressure at 0.3. So pressure at 0.2 is going to be equal to gamma of this manometer fluid, which is just a gauge fluid. Let's call it F, multiplied by this height, 0.6. 0.6 plus P3. So we have P3, we have P2. Let's plug that in. Let's put P2 first. P2 is going to be P of A plus gamma of water, 1.1, right? It is equals to gamma of fluid multiplied by 0.6 plus PB, this is P3, PB minus gamma of water, 0.8. So you take B to the other side, you take this to the right-hand side. You have PB minus PA minus PB, right? We have gamma for water. We have the specific gravity of the fluid is given to us, the millimeter fluid. Should be able to find whatever you need to find. Okay? Okay, so let me ask you this question. Let me ask you this question. Was this exam a hard exam? Yes. We have one yes. How many yeses do we have? Okay, we have one so-so. Who thinks it was an easy exam? No one. Okay. Okay. In my mind, of course, I mean, I've been dealing with this material for more than a decade now. So this is, it doesn't really matter how hard is the level of exam. It's going to be easy for me. But I have to understand what is hard or easy for you. In my mind, this should have been a very easy exam, right? That's why the communication is the key. You have to make sure you ask me about your questions, right? Okay. I thought this exam should be a very easy exam for you, right? But apparently it was. That's all right if it wasn't. Just have to make sure you. And I keep saying this from the beginning of the semester, and to no avail. But just keep the communication line open. Just talk to me. If you think the homeworks are hard, you have to talk to me, right? You have to tell me. And okay, so which question was the hardest question? What do you think? And I want every one of you to have an input on this. So everyone should tell me a number.
I think 9 was.
9. Which one was 9? Okay. Can you like elaborate? What was the hardest part of this? Like which part you were stuck? Which was the thing you couldn't figure out, or was it the whole thing? Oh, 9.
Yeah, I just forgot, like, you had to, like, take the derivative.
Okay, taking the derivative.
I just didn't really see that at all, so it made it tough to find, like, the answer.
Okay, that makes sense. Okay. What else? Do you want to start from here and then, because I want everyone to jump in, right? And there's no wrong answer here, so.
For me, it was probably 2.
Okay, okay.
And that was probably just because I think because it said to give the answer in Pascal. So I figured because we weren't given the modulus, both modulus, I figured like that wasn't a route I could go down.
I understand.
They wouldn't give a specific answer.
Okay. But actually that makes a lot of sense. And if in the next exam you were having this kind of thought, make sure to ask that from me, right? Because that's the difference is going to, I mean, getting the full points, all of the points of a problem and getting nothing, right? Just one very simple question. Let's go from there. Number 9 again. For the same reasons? Yeah. Okay, taking the derivative. Okay. We can definitely work on that a little bit, just the mathematics of it. Okay. Okay.
Mine was probably number 2 or 1.
Number 2 or 1. What was about number 1?
I don't know. Number 1, I looked at it and I just didn't recognize anything. I mean, looking at it when you went over it, it made
sense, but during the exam, looking at the equation, I just couldn't pick out anything that I recognized.
Okay.
And then number two, I just didn't know where to start. I mean, looking at it with the bulk modulus, I mean, that seems pretty simple, but I just didn't know I needed to use that.
Yeah, I see. So for number one, whenever you are, I mean, if I ask you to like figure out whether something is dimensionally homogeneous again in the next exams, final or exam, I mean, we're not going to do that on exam 2, but if I ask you to do this on the final exam, the equation may look very like different, may look like a very complex equation, but that doesn't really matter because you don't have to solve an equation, right? You have to make sure that you understand that the dimensions. If you don't know the dimensions to something, that's all right. You can always ask me what is the dimensions to. I don't remember the dimensions to most things myself, right? And I don't ask you to do so. So if you don't remember the dimension to something, you have to make sure to ask, okay? And do you have the same reason for number 2 as
Yeah,
what?
Number 2, I just didn't know where to start.
Okay. And I mean, even if you don't know where to start on an exam, that's also a legitimate reason to ask questions. Don't be afraid of asking questions, right? Again, you are here to learn. Taking an exam is part of the learning experience, right? Number 10. So you didn't know where to start with this. Okay. So you couldn't think of the Bernoulli's equation for this problem. Okay. And that, I mean, the nature of the problem may be that like maybe since it's a flow over an airfoil, and we usually talked about flow inside a pipe, I can understand that. But that's also, again, you always make sure to ask me questions, right? I don't know where to start. That's a perfectly legitimate reason for asking questions in the exam at any time, not just in the exam, any time in this class. My goal is for you to learn. Sometimes learning in an exam under the stress is the best way to learn, right? So asking a question, I probably won't give you the answer, but I tried to guide you I mean, I could have told you that you should use Bernoulli's, right? I guess that would have helped a lot, right? If you know where to look, you probably could have found the solution. You said your question, right? Do you have any other questions? Okay.
Mine was probably 1 or 2 because I didn't catch the way you did the derivative on the first one, and then like I just couldn't figure out the second one.
Okay. Yeah, we probably could have solved more example problems on the bulk modulus. Okay. Okay.
For me, it was also 1 or 2. For 2, I just didn't think to try and use bulk modulus for it, so I tried to do something completely different, and that didn't end up working out, obviously. For number 1, I just saw it and was like, what am I looking at? Didn't quite know what to do with it, so that's why I got that one wrong. I should have gone and asked something.
Okay, I can see that. Asking questions always goes along then. We also have an online comment that says it was a fairly challenging exam. Okay, that's good to know. I didn't know. Coming in, I thought that not everyone, I met a lot of people will get an A, which is, you of course have the option to make up for it. And this is my first time teaching this course, so I don't know how much people know when coming in.
Probably 2.
Probably 2.
Didn't know where to start with it.
Okay, that makes sense.
I'd agree with that. I could start off every other problem, but I didn't know how to start number 2.
Okay. That makes sense.
Mine was either 2 or 10. For 10, I figured that I needed to use Bernoulli's equation, but there were like 3 different units, and I didn't know like conversions and stuff. I just got confused, and I think I just got too much in my head. And then for 2, I took the assumption that liquids are incompressible, I guess, too far. So I sort of thought that it was like a trick question, and that like you didn't have to do anything.
Okay.
So
I can understand that. Yeah, that's so. That's actually for number 2. That's an assumption I thought some people may make, but then my idea was if they make that assumption, they will think that this question doesn't make any sense, and they will ask me, right? So, and I will explain to them that this is not an incompressible case. You should do the compressible analysis. But I can see where you would go wrong with that, because we always assume with this is a very good assumption that liquids are incompressible, right? We don't usually deal with compressible liquids that often, at least in this course. Okay, and for problem 10, that you brought up a point that I think I need to mention, and I can't say this enough, that you are allowed to bring an equation sheet. That if you forget an equation sheet, you are not going to be punished for it. You can ask, right? I didn't think of this equation. I mean, what was the Bernoulli's equation? Whatever that equation is. I mean, you may ask me to give you the wrong equation for a specific problem. I will give you that wrong equation, right? Whatever you need. But not knowing the conversion rates, not knowing the equation is not something that you are being tested on in this class at all, right? I don't really want you to memorize any equations or any conversion rate, because it doesn't make any sense, right? Because, I mean, no one really, in your future, no one is going to expect you to memorize something, an equation or conversion, right? So if you don't know any of this, you can always ask. You should, right? It is going to be your loss if you don't, okay? I think we only have one person left. The derivative. Okay, so let's talk about that a little further, since we already spent a lot of time. Are you going to upload the full solution to the exam? Not at this point. What do you do in the live stream, or just what do you do in the live stream? So we have one question. This is the question. Let me read it to you. Are you going to upload a full solution to the exam, to the Blackboard, of the exam to the Blackboard, or just what you do in the live stream? So since you have to submit the solutions to this exam, I at least want you to go through the live stream if you are not present in the class, and see the solution procedure, understand the solution. So I'm not going to upload the solution to this at this point, right? After next week, we can definitely upload the solution to the exam, right? So yeah, at this point, no. You only have to use the live stream. Well, since we have already spent most of all of the class on the exam, and I think this class was a fruitful class. I think we learned a lot about the expectations of the course, and you hopefully you understood the material a little better, right? Let's talk about this, and then I will let you go. So I heard a lot of comments, but the things that is a little harder for me to grasp. Let's see. Okay, I just wanted to know that. Yeah, it will eventually, the solutions will eventually be up there to the exam problems. Yeah, that's for sure. There are some of you said, and I mean, I know just a couple of you said this, but it was a problem with a lot of 75% of the students, right? That they couldn't figure out that they have to take. So I had the equation. A lot of you had the equation in problem number 9, that tau is equals to mu du dy, right? But you couldn't take the derivative, right? So it never occurred to the students that you have this equation, and we know, and we have the main equation is tau equals to mu du dy, and we also have the equation for velocity, right? And I have a hard time understanding why is that the case. Why couldn't you make the connection? Because if you didn't know the equation, yeah, that's understandable. You could have asked me during the class, the exam. Next time, make sure to do so. But a lot of you put down the equation. So we had this equation in the sheet here, which is also the case with this exam that I have in front of me. But and we also had the the function for u, but it never occurred to people to take the derivative. And I mean, if you can add something to it, if you can tell me why you couldn't make this connection, so we can work on this. Right? The reason I'm asking is I want to work on. I mean, maybe we can go back to the mathematics of it and talk about the mathematics a little bit, right? So why do you think that was the case? Why people couldn't make the connection? What was the function? 2yh minus y squared divided by h squared. Do we have any ideas? Why there were some of you who didn't, a lot of you, not just some of you, who couldn't make this connection, who couldn't see that the only thing you really need to do is to take the derivative of this velocity function. Any ideas? Any comments? Or what can we do to help you make that connection in the future, right? In the future exams, in the future courses, in your future life as an engineer, if you ever had to take a derivative. Okay, that's, yeah, let me know, send me an email if you had any ideas. If not, then I guess we just have to take more derivatives, right? Do a little more practice on taking the derivative. I think the problems we solved in class was very, I mean, definitely your homework is much more complex than the exam, right? And the problems we solved are more complex than, very more complex than the exam. So I focused on, I wanted to do the most complex thing, and I was under the impression that if you understand the most complex thing, you should figure out the simpler problems. But I guess I think that makes a lot of sense. Actually, I shouldn't have made that assumption. That was a wrong assumption. So moving forward, we'll try to solve some basic examples using just the plug and chug type of problems, and then if we had enough time, we will move on to the more complex problems. Okay. So we'll see. Hopefully, we all get a very good grade out of this course. I mean, you all. I'm not going to be graded, but you all will get a good grade out of this course, and we'll continue the discussion on the conservation laws in the next lecture. We only have to cover all of the basics. We only have to cover 2 more chapters of the book, chapter 5 and chapter 7. If we had enough time, I'm going to cover chapter 8, then come back to chapter 6, right? But if not, I think we'll be fine. We'll definitely be able to cover all of this, but we'll see how it goes. Have a good weekend. Yes.
You post the chapter 5 notes too.
Sure, yeah, definitely. I'll make sure to do that.